um, because I want to make sure that even the people who can't be here live um, can hear the announcement stuff. No, I don't want that. Sorry, I'm trying to bring up. So I've gotten some emails from people who are concerned for various reasons. And so I wanted to actually spend a couple minutes and sort of maybe assuage some fears, right? Because the natural thing to do is, people are looking at the homework and being like, wow, this is really hard. I don't understand it all. I don't know where to begin. And then panic sets in, right? So I've gotten a couple emails that are like, I'm not going to pass this class. I'm really worried. And I want to say sort of flat right from the get-go that is completely and totally untrue. There's only one way really to not pass this class, and that is to just not do things, right? I find it hard to believe that someone who actually attempts to work through all of these exercises wouldn't learn enough by doing that to at least have a passing grade, right? I've gotten emails basically that, the homework is hard. Well, yeah, it is hard. And that's by design, right? This is the start of your junior year. So you've had 2 years under your belt. And this is the change, I think, or it's really important to me that this class helps you guys foster the skills that you're going to need either in your future career, right? Either that's on the job thinking or a future in graduate school, where the focus is actually on thinking through something new, solving a new problem, and working through it. And I understand that not everyone is going to be good at that right from the get-go, right? This is, for some of you, it might be the first time you're seeing assignments that are significantly different than, say, what you had in calculus, right? Where you learn a procedure and then the homework in the exams is, can I apply this procedure, right? Can I demonstrate that I know how to apply the process that I've learned repeatedly to a large number of problems, right? And in a lot of classes, that has a lot of value. My objectives in this class is not to teach you a process of how to do things, right? My goal here is to get you to understand the theory and think about a problem, right? The actual quantitative answer for most of these homework assignments is not all that important to me. What is important to me is that you guys begin to demonstrate a proficiency in thinking about materials in a way that demonstrates expertise, in a way that you can understand what is happening and what is going to happen, right? And I really don't care if you come up with an energy of a specific number to two significant figures, right? In fact, you know, you can get 99% on all of these assignments and on the exam from order of magnitude type calculations. And so I really am saying this, I really want to say this because I don't want people to be panicked. I want people to understand that yes, these assignments are difficult, right? I think, you know, if Kelsey and Alexander are on, I think they will confirm that it's probably difficult for, you know, at first glance, for them too, right? And
absolutely.
Right, and that's not a dig on them, right? It's just because I'm asking questions in a way that is a little bit different, right? And I want you guys to spend time and think. And the other thing is, I don't expect you guys to struggle through this on your own, right? Spending time and working and wrestling with something is great, right? When it's productive. What I really don't want is someone sitting there by themselves in abject frustration and spending hours not even knowing where to begin, right? And so if that's the case, if that's sort of where people are finding themselves, I think a lot of it has to do with the isolation of sort of COVID times, that there isn't the fourth floor of Watts to gather together and talk through these problems. So, you know, I urge you, I kind of want to people to work together on this, right? So if that means some Zoom study groups, there's a discussion group on the Carmen page set up for homework, right? Utilize that and talk about it amongst yourselves, right? So just real fast, I want to run through a couple points on the homework here, right? And I also want to make the point that if you find yourselves doing a whole lot, then something's not quite right. So all of these problems in and of themselves have fairly simple calculations once you get to where you need to be, right? So it doesn't, none of them should really, you know, have pages of mathematics, right? Okay, so question one, right? I specifically state that I have the regular solution model, so our omega term here is 2 times 10 to the 4th, right? In their pure form, they both take the crystal structure alpha, right? So if they both have the same crystal structure, there's really only two two ways the phase diagram can look, right? Most of the time, right? And anyone have an idea what we can what it can potentially look like?
I drew it as basically one solid parabolic curve as a function of composition, with it peaking somewhere in the middle. Entropy.
What's a parabolic curve?
An upside down U.
Oh, you mean the Gibbs free energy,
I
or
was plotting
the phase
as
diagram?
it makes it. Oh, the Gibbs free energy is a function of composition. Whoops. Oh no, wait, it was the entropy, the delta S.
Yeah. Okay. So I was asking sort of a higher level question first, right?
Oh, sorry,
what
my bad.
are potential ways the phase diagram could look like? Right. But since I have Kevin's on the hook already for opening his mouth, I'll ask him.
Okay, well, actually, if you want to about a phase diagram, okay, well, first off, it's still going to have a liquid phase because alpha or not, it will melt at some point.
Yep.
It will have an alpha region at closer to A. Actually, won't it be just a solid alpha region along the bottom then in that case?
It could have a solid alpha region depending on what the Gibbs for energy curves look like, right?
Mm-hmm.
And then as we get lower in temperature, it could phase separate. So it could have a spinodal region on the bottom, right? Depending on the value, if the heat of mixing is too high in the solid, it could phase separate into two alpha regions with a miscibility gap that extends all the way up, right? In which case we would then have a eutectic structure.
I think I have a vague idea. Could you scroll down to that phase diagram right there for a second? I want to kind of like show something.
Yeah.
Instead of having like this beta here, I think it's going to look almost more, I want to say, symmetric maybe. Like it'll have like a corresponding alpha region on the other side.
Yeah. So you mean, let's take a.
Like with mirror symmetry in the middle is what I'm saying?
Yeah. Largely because of the way the regular solution model works, right? We would probably have a phase diagram that looks potentially a lot like this.
That's what I was going for there.
Right?
Only instead of having beta, it would be like, you could call it alpha B or alpha A.
Alpha, right? So these could potentially be two different alpha regions, right?
Mm-hmm. And depending on the temperature, this you can't see what I'm pointing at, but the whole that eutectic line, wouldn't it like basically go, I want to say down and down or closer to.
Yeah. And so if this becomes a smaller hump, right? Mm-hmm. If the free energy of mixing, I mean, if the entropy of mixing is in the small enough, right, you'll get a hump here where you've got complete solubility at higher temperatures from mm-hmm. alpha all the way across, right? And then you've got a miscibility, a spinodal region in here where you have a miscibility gap where it can go to alpha and alpha prime, right? So
would that necessarily change the melting temperature as well, or?
No, not necessarily, right? Right, not directly at least, right? So there's essentially there's not a lot of ways that this sort of phase diagram could look, right? And probably you can guess that the way I asked the question is that we're not going to have complete solubility, right? Because I asked about two different temperatures, And if you notice on Carmen, I said I screwed up when I did the conversion, and this should be 296 and 790, 292 and 792.
So this diagram would be most useful for B, correct? For part B, this phase diagram.
Yeah.
But here's the problem I'm having.
Okay.
I get this conceptual diagram here. What I don't get is how to use that 1,000 temperatures to get anything concrete.
Okay. So let's talk about that, right? So first, let's just start with A, right? So we have this entropy of mixing, right? I asked about. Right? I don't give you anything about entropy, right? So then we have to look at what else we say. Well, I did say it's a regular solution. So what's the entropy term of a regular solution look like?
RT XA ln XA plus XB.
Right. So it's just exactly the same as for the ideal solution, right? So it's just purely a configurational entropy based on the way you can arrange the atoms in the solution, right? So it's just going to be XA ln XA plus XB ln XB, right?
Oh. No, like RT. That's
yeah, the RT, right? I'm just saying the configurational.
Okay.
Right.
And okay, so here's another thing. I went back in the textbook and like back to our old reading. This took me a bit down memory lane here. I found that this whole delta HM finding the whole sigma, what do you call it? The omega XA XB to help simplify this equation.
Yeah.
But I still couldn't find out how to get like a firm entropy equation from that. So I just did the plots. Like generally.
Okay. Yeah, that's fine. Right? I mean, it's going to be, you can do fairly schematically. So I mean, the equations, let me just open the book so I can point to exactly where the right, so the right, so equation 125 in your reading, right, is essentially right where the entropy term, the term is. And so the entropy of mixing, right, is essentially, as Kevin said, right, so that's just going to be a function of XA and XB, right? Of course, XA and XB are not independent, right? We know that they have to sum to 1, right? So you can easily replace XB with 1 minus XA, right? And now you have everything in terms of one variable. And so the first part of A is just plotting essentially equation 125, right? And the entropy itself is independent of the temperature, right? It's just the number of configurations, right?
Temperature, I believe, just alters the height of the curve, I believe.
Well, it doesn't affect the entropy curve itself. It affects the contribution of entropy to the Gibbs free energy, right? Because
okay,
Gibbs is delta H minus T delta S, right? So that's where the T comes in. But the entropy itself doesn't have any temperature dependence, right? And so then the Gibbs free energy is just, well, we add the free energy or the enthalpy of mixing, right, minus T delta S, right? And essentially we plot that, right? And at the
you
lower
substitute
temperature, right? And what we'll see is that at the lower temperature, the Gibbs free energy is essentially positive everywhere, right? Except for two tiny little regions at the end. And then at the higher temperature, right, you get a clear symmetric double well, right? And so then I say this is that should be 776 or whatever, determine the composition of the two phases at equilibrium. Well, what's going to determine that? Right? This is exactly what I said. This is the most important figure in this class, right? The common tangent, right? So I've got two minima, right? And because it's a regular solution, what do we know about those minima? They're symmetric, right? So finding the common tangent is actually really easy because it has to be a horizontal line, right? That connects the two minima of those curves, right? If one was higher than the other, then the tangent's not exactly at the minima, and it makes it a little bit more tricky. You have to find where the derivatives are equal to each other, and it's a little bit more involved mathematically. But the big picture understanding of applying the common tangent works fine here, right? And then the inflection points or the spinodal points are where the second derivative of the Gibbs free energy equals 0. Right? And then what about part C? Here we're not working at a fixed temperature, but we're working at a fixed composition, right? So in this case, we fix the composition, plot Gibbs free energy as a function of temperature, and find out where it goes negative. So at any temperature higher than that, the free energy is negative. So you're going to have complete solubility. At a temperature below that, where the Gibbs free energy is positive, you're going to phase separate. Right? So there's nothing, when you break it up, this problem is pretty straightforward. The key, and what I'm trying to get you guys to learn through time and practice, is how do I break this up, right? How do I think about it in small chunks? Because that in and of itself is a skill that has to be developed, right? So, okay. Okay, so question 2, right? So we've got this phase diagram. What I wanted to throw this in here is because the paratectic wasn't explicitly addressed in the reading, right? And thinking about paratectic points the paratectic point is pretty important for the welders, right? Who have to deal with spend a lot of time thinking about welding in ferrous structures, right, where you've got a pretty important paratectic point on the iron-carbon phase diagram, right? So what do the free energy curves of the various phases look like, right? And if you look at the examples of the eutectic and the examples in the reading, this becomes a pretty easy problem, right? So we're going to do two temperatures, one that's just above, or three temperatures, right? Where we have this two-phase region, alpha and liquid, right?
Could you tell me where in the reading to look? I was a little lost trying to find this last night.
So the examples are figures like 130, 131, and 132.
Thank you.
Right? So if you take a look at those, it shows you essentially how to go from the Gibbs free energy curves to the phase diagram. Here I'm saying, look at the phase diagram and give me a schematic of what the free energy curves could look like, right? And there isn't a unique answer here, right? But we do know here, I've got three curves I need to deal with. I need to deal with alpha, beta, and liquid, right? And at the higher temperature, at 1300, I have a region where alpha is stable, a region where liquid and alpha is stable, and a region where liquid and alpha are in equilibrium, and a region where the liquid is stable, right? In the region where alpha is stable, right, I need to make sure that I've got two curves, right? I've got an alpha curve and a liquid curve. My beta curve should be above the other two. And I'm going to have a common tangent that intersects alpha and liquid at about 10% and about 60%, somewhere in there. Right? If I'm below, now I need three curves. Right? I'm going to have a common tangent between alpha and beta, and a common tangent between liquid and beta, and a region where liquid by itself is stable. Right? And if I come down here to 900, now my liquid curve is going to be high, and I only have to think about what the common tangent between alpha and beta is going to look like. Right? So take a look at those figures. Yeah, so Giacomo makes the point, right? For this schematically, I don't care about the actual relative heights, right? As long as you draw it so that the common tangent's in about the right spot, that's all that matters. Right? Highly schematic. Right? So this is a question that when you first start to think about is going to take a little bit, but when you sort of internalize it and conceptualize it, this is a 5-second question, right? Literally just make a couple quick sketches, right? And thinking about energies from the phase diagram is an important skill. Okay. Question 3, I think, is probably pretty straightforward, so we can sort of skip over that. Question 5, question 4 is kind of conceptual. Question 5 is one that I think is probably causing people some grief, right? And so,
For those who are wondering, there's a very good slide in lecture 9 for question 5.
yeah. Are you asking what is a good slide, or is that there is a
I was just informing it. Someone asked me about it the other night from my lab group.
Yeah, right. And so, and again, what you need is directly out of the reading here. So if you have the green version of the book, which is what I have, which is like my main reference that I've had forever, and have things marked up, right? And you can actually see these are markings from when I was an undergrad, right? When I read. So I've had this book for this version for a long time, and I actually reread this book cover to cover when I was studying for my candidacy exam as a PhD student. So equation 160 and equations 158 in the green version are really what you need. And I think the equation numbers are pretty similar in the purple one. I just don't have that version next to me. So basically I'm asking, how does Gibbs-Thompson affect both the free energy, right, which is just the surface energy term essentially, right? I now have extra free energy in my system due to the fact that I've got this an interface with a given surface energy associated with it. And then I also asked how that's going to change the composition. Well, the extra change in Gibbs free energy alters the chemical potential, which then alters the composition, right? And in the book, they work through all the derivations of how that chain of logic goes, but then they give you an expression that basically just says what the composition is going to be. And one thing to pay attention is if you look at the true expression here is 160, right? I think, is that coming up on the screen backwards? I don't know. Right, so 160 with this exponential term. The approximation here is specifically for small values of the exponent. So you have to think about this, do I fall into the small value case, or do I just use the exponential equation, right? Which is valid everywhere, and that you have to make sure your units are consistent, right? Right. So make sure that you've got atomic volume versus molar volume, right? Things are in joules, not millijoules, right? You just have to, apply your dimensional analysis. Okay, so that's A and B are pretty straightforward. C is a little bit difficult, right? I think I'll sort of actually just go out and say it that C can be quite challenging unless you know how, until you figure out how it's done, and then you're like, oh, that's pretty obvious. But when you're first working through it, this can be a real bear in understanding, right? So I'm going to ask anyone other than Kevin to talk to me about C.
Thank you.
And it's okay if your answer is I don't know. But someone who's not afraid to admit they don't know how to proceed, and we can talk through it a little bit.
Is part one that it's like Ostwald ripening that's occurring?
Yeah, so is this Giacomo?
Yeah.
Cool. Okay, so yes, right? So we do have Ostwald ripening, right? So for I, what's going to happen? So just say it sort of colloquial or in common language. What's going to happen?
The smaller particles will coarsen and like become bigger particles.
Um,
I guess they'll like join up a little bit.
So what's gonna happen is the small Ostwald ripening, right? We have the smaller particles are going to dissolve and the bigger particles are gonna grow.
Okay.
Right?
Yep.
Right? Why is that gonna happen?
Because it's more energetically favorable.
Right? Yeah, it's more energetically favorable because of the Gibbs-Thompson effect, right? The higher free energy of the smaller particles. Right?
Yep.
Okay, so if we have that, what about the change in energy of the system, part two?
Would you, I guess, essentially look at the distribution and like do the same kind of calculation in part A, but apply like the ratio of like 3/4 of them will 3/4 of that change will be from the 10 nanometer particles, and then maybe the other 25% is from the 10 micron particles.
Yeah, but we can actually really simplify this problem a lot, right? So,
Okay.
right, if we think about it, right, I've got 10 nanometers to 10 microns. So that's a huge change in the relative size of each of these particles, right? How does the volume go with radius?
I guess like as you increase the radius, the surface area to volume ratio decreases.
Well, let's leave
The
surface
volume
area
increases
out of it, right? I just have a sphere of a given radius. What does the volume, right? How does the volume depend on the radius?
It's a cubic function.
It's a cubic function, right? And I have three orders of magnitude difference in the radius. So if I cube it, how many orders of magnitude difference do I get in the volume?
Like 9.
9, right? So will adding these these particles here to the bigger ones, will it really change their volume or the amount of surface area that they have?
Probably not at all.
Not at all, right? So it turns out if you calculate it, right, if we assume that we have 1 mole of beta here, right? Just for convenience, assume that we have 1 mole of beta, and you calculate the relative contribution, even though these 10 nanometer particles are 75% in terms of number, there's 3 times as many of them, they only take up 1/billionth of the actual amount of atoms, right? 10 to the minus 9th moles of beta are in these small particles. The rest of it's in the big particles. So we can completely ignore that any change bringing in these to here, right? So we can say that the energy of the big particles is going to stay constant, right? Because we're only adding a billionth to their size, right? Which means we're only adding a millionth to their surface area, right? And so if we do calculations to 3 significant figures, the change is going to be orders of magnitude less than our estimate, right? So we only need to be concerned with what's going to happen to the energy of our system. So we need to calculate what's the increase in the energy of the system due to these 10 nanometer particles, right? And how much energy we gain when these go away, or how much the energy of the system is decreased when these particles go away, right? And so right, so so first off, we just need to figure out how many particles we have, right, in this 75%, right? It turns out we have quite a bit. It turns out to be like a billion, right? 10, both of the numbers of particles are like 10 to the 9th, right? The small particles are closer to 10 to the 8th, and the big particles are closer to 10 to the 9th. I mean, the small particles are closer to 10 to the 10th, and the big particles are closer to 10 to the 9th. I said that backwards, right? So we've got some large number of particles. So we just calculate the total, the surface energy per each particle, multiply it by the number of particles we have, and that's going to be the energy change when they go away. Right? So it's not there's nothing difficult sort of in the calculation. It's just what's the chain of logic to get me from A to B, right? And I know there's a chunk of you out there that even on hearing talking about how to work through the answer is still saying to themselves, well, crap, I never would have thought of that, right? And of course not, right? If it was obvious, I wouldn't assign it as a homework, right? You know, these questions are by nature hard, and I really don't expect everyone to get perfect scores on the homework questions, right? Not doing perfectly on the homework does not imply to me that you are not getting the material, or that you're not going to do well in the class, right? I'm expecting to have a pretty big curve, right? I ask questions that vary in difficulty because I want things to differentiate, right? I want to see the spectrum between the students who are clearly all right, and this is like they were, you know, this is their jam, and they're going to be brilliant theoretical material scientists, right? And then I want to also be able to identify who needs help, right? Who do we need to spend some time talking about these ideas, right? Because their skills as a materials scientist lie in a different realm, right? And what's the spectrum in the middle, right? So maybe that's kind of a new concept to people, right? Is that I really don't expect everyone to get all of the questions completely correct. Yes, I will be posting the solutions for homework 1 and the grading rubric this weekend, and the grade should be out early next week. Right? So, okay, so I've taken most of the time talking about this today, right? And I definitely don't think it's a waste of time, right? Especially if it helps people feel more comfortable and more confident, right? So just the last couple minutes, if you're really struggling, right? Keep in mind that that's okay. What are the steps? Well, first, right, talk to your peers, right? I want you guys to work together and talk together about this, right? That's where some of the best learning comes from, is working through things with friends and colleagues, right? Come to the office hours and don't ever feel that you can't email me with a question, no matter how silly it is, right? Or how silly you think it is, right? I really want to hear from you guys if you're stuck, right? I'm not giving you hard things to do to lord it over you, right? And be like, oh, my students don't know crap. Because that's definitely not true. I'm giving you hard things because I want you to learn and grow from them. And if that means I need to spend some time with some of you in one-on-one instructions or offline Zooms, hit me up. I'm happy to. So don't ever be shy about asking me a question, right? Even if you don't know how to phrase the question, it's okay to just say, send me an email, and send the TAs an email and be like, I am completely lost on this concept. I don't even know how to properly formulate a question or what I should be doing. Right? That is a perfectly okay starting point. Right? What isn't okay is to just be like, I don't understand this, so I'm not going to do it.
My policy is the same as what I used back in the Math 1172. Write down the equations, try to go through the process, and you'll get some points.
Some points, right? Yeah. The thing is, a little bit differently is, I think there are times where people can look at these questions and just not even know what the first step of what the equations are, right? So I would say the analog to that would be look at the question and try and figure out what are the big topics that I'm potentially asking about, right? So if this were question 5 were an exam question, let's say, simply starting out by saying, okay, this is obviously related to the Gibbs-Thompson effect, right? Let me go and look what are then the equations of the Gibbs-Thompson, right? Do I see anything that relates to composition? Do I see anything that relates to Gibbs free energy? Right? And so, that's sort of where I would start. Start with see if you can identify what is the concept that I'm trying to get you to think about through this question. Okay, so because I had to make some changes, right? The homework for this is due Wednesday, right? Which means that we got TA office hours this afternoon to help. But again, if you're stuck, shoot me an email over the weekend. I'm happy to set up another time to meet on Monday or Tuesday with people who are struggling. Okay? So hit me up, hit the TAs up, and most importantly, talk to each other. Okay? So, anyone have any last minute questions? It wasn't originally my intention to spend all day talking about this, or all lecture talking about this, but I think it's worthwhile. Okay, so if everyone's cool, I'm gonna give you back a minute and a half. So take care and have a good weekend.